Okay, so in our last class, we talked about what is ductility, right? We mentioned two different equations you can use to calculate what is ductility. Remember that? Let's do a quick review. One is based on the percent elongation that depends on the change final length, the length at fracture minus the original length divided by original length times 100%. That tells you the percent elongation. Another way to calculate ductility is percent reduction in area. That's percent RA. Then you have to find out what is the cross-sectional area at fracture and find the change of area divided by the original area to find out this percentage. Then after that, we mentioned resilience, the modulus of resilience. How to calculate modulus of resilience is to find a simple way to do that is to find stress strain curve of the material and identify where's the linear region, where's that yielding strength, and simply find out what is the area of that triangle. That is your modulus of resilience. I just want to do a quick discussion here. How many of you have a car? Okay, I think most of you, and you probably drove a car before. And what part of your car needs very large resilience? I mean, what materials in your car that needs high resilience, modulus of resilience? You have 2 minutes, discuss with your neighbors to come up with a part that needs high resilience. Okay, any answers? Which part needs, the material made that part needs high resilience? Think about the definition of resilience. It's a capacity of a material to absorb energy when it's deformed elastically. And then upon unloading, it releases this energy. Suspension, that's a good example. The springs in your suspension, you want that spring to absorb all the energy for its elastic deformation and release it, right? Any other parts needs high resilience. Any other answers? Frame? Why frame needs high resilience? Twisted, it can come back, the flexibility of the car, the chassis, right? That's important. So all the concepts we learn in this chapter, mechanical properties, can relate it to the car you have. And so next concept, we're going to talk about toughness. What is toughness? Whenever we say, oh, this material is tough, what does that mean? Is that the right statement? Can we say steel is tough? Or diamond is pretty tough? We're going to learn what's the definition of toughness. Okay. All right. That guy wants to learn some toughness, huh? Okay, so toughness is the ability of material to absorb energy and plastically deform before fracture. The definition is a little bit similar to resilience of modulus of resilience. All right, the keyword here, it's plastic deform, plastic deformation. Previously, the definition for modulus of resilience, it's the definition, deformation under the linear region, which is the elastic deformation. But here for toughness, the definition has to be plastic. And sometimes it's also called modulus of toughness. So this toughness can be measured by impact test. If we have time, we'll find a video for that. Okay, and from your stress strain curve, you can find out this toughness easily. Okay, if this is a stress strain curve of a material, the toughness, it's just the area under the curve. That's it. If you can find out what's the area under this stress strain curve, and you can find out toughness. And previously we mentioned resilience, modulus of resilience, it's only the area in the linear region, right? But now the toughness covers that part and go beyond. It covers all the area under that curve. Now I have a question for you. How to calculate that area under that curve? What? You can do integral if you know the function. What if you don't know the function? What? Riemann. Just do estimations, like make this diagram into a very small grade, like you put small grade, right? And you count how many small squares you have. If you have all these squares in the uniform size, if you print this on an engineer paper, you can count how many grids you have and kind of times the area of each grid to find what's the area. Now you can get what is toughness of this material. Or maybe if you have computer software, everything is written for you. As long as you have the curve that calculates what's the area underneath the curve. So that's the toughness. And one interesting thing I want you to look at is, I want to compare two materials. Okay, the first material, let's call it material A. The second material, let's call this material B. First, I want you to compare these two materials. Just look at the stress strain curve. Which material is more ductile? A or B? If this B, raise your hand. A, raise your hand. Okay, now probably haven't heard my question. Which material is more ductile? From just by looking at this curve. You don't need to do any calculations. Just by looking at this, not ductility. Well, you can see that too. Will tell you which one is more ductile. But just look at the curve. Which material experience larger deformation before it breaks? A or B? B. Then of course B is more ductile than A, right? Okay. Then how about yielding strength? Which material has higher yielding strength? A or B? A. Yeah, A has more yielding strength. Large. Yielding strength for B, it's probably somewhere around here. For A, I don't know, pretty linear. Maybe it's somewhere around there. And how about the fractional strength? Which one is larger, A or B? So the strength at fracture. A, right? A is up right there. But for B, it's pretty low. How about ultimate tensile strength? A is definitely stronger. Okay. And my question for you is, which material is tougher? See? So you tell me all of those strengths, A is higher than B in at tensile strength, yielding strength, fracture strength. But B is tougher than A? Yeah. So now you know the correct definition of toughness. Because if you do, you count the area, material B has larger area than A. So the toughness of A is smaller than toughness of B. All right. You can see material A is maybe stronger, right? You can use the word stronger or maybe stiffer. Why A is, can we see A is stiffer than B? Why? Which property is related to the stiffness of a material? The modulus of elastic modulus or Young's modulus. And that's the slope of that linear region. A has a steeper slope than B, so A is stiffer than B. Yeah. Okay. And which part of your car need to use tough material? Need to use material that has high toughness. Two minutes, talk to your neighbors. Think about which part you need to have high toughness.
Going through the windshield.
Okay. All right. So it seems like Anywhere you don't want it breaks, you have to use something tough material to make that parts, right? For example, axles of your car, you don't want that break easily, so you want to use a tough material to have the energy absorb all the energy before it fractures. Okay, let's find the video. We can find the impact test video. Okay. Okay. So in order to test what's the toughness of a given material, you can do an impact test. Let's look at how the impact test is being done. Share screen.
The standardized chartered impact test has been designed